Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem today. We're going to tie up our unit on electric fields, capacitance, electric charge, all that kind of stuff. It's kind of the static electricity piece. And we want to talk about this concept called capacitance. It comes from the word capacity. So it's like how much something can hold, right? Your body can only hold so many calories of energy or something like that. It's a capacity, right? So we're talking about capacity, though, of energy in electrons. Remember, electricity comes from electrons. They come from electrons. So in the world of electricity, there's something called a capacitor. All right? This is a device that holds charge. Think of it like a big bucket. And the bucket's how much charge you can hold, which you can save to do some cool work. And ultimately, a capacitor is where you have two plates separated by a distance. And one plate, so they're oppositely charged. So one side's positive and one side's negative. So it's like a plate, like a little metallic plate. There's a gap between here and here. This side's positive, this side's negative. And you can increase your capacity depending on if you move it closer or further, or if you add more charge, positive or negative. Basically, the two big things is the distance between and also the charge itself. Now, at some point, the idea, of course, is the capacitor can hold charge, but eventually the charge will build up such that it will jump. The electrons will move across the gap, and whoo, all the energy gets used to a certain point. So that leads us to what is capacitance. Like I said, think of capacitance as the total amount that you can hold, and it probably doesn't surprise you that it has to do with how many, the capacitance equation, for lack of a better, C, capital C, not to be confused with Celsius, is equal to Q over V, where Q is the charge and V is the voltage or the electric potential. And if you think about it, the Q is going to be in coulombs per volt. So it's coulombs per volt. So how many coulombs you can have, how many moles of electrons in charge per every volt. So this is how much you can hold. So let's do this quick example, right? If I got a 0.75 let me back up. And this unit is often simplified as a F, or as a Faraday. Now don't confuse F with Fahrenheit. This is Faraday, named after the great, famous, amazing physicist Michael Faraday. So let's take a look at this example super fast. If you've got a 0.75 microfarad capacitor, it is charged to 16 volts. What is the magnitude of the charge in each of the plate of the capacitor? It's asking for the capacitance. So you're going to take, no, you're not asking for all of that. You've got the... So let's do this crazy quick example. We've got the 0.75 microfarad capacitor charged to 16 volts. What is the charge, right? We're solving for Q in this case, right? So we know the capacitance. The capacitance is 0.75, I'm going to say this, times 10 to the minus 6 Faradays, right? Now, C times V equals Q, so I'm just going to multiply by the voltage. The voltage was 16 volts, and you multiply these two numbers together, and you get your answer. This is 1.2 times 10 to the minus fifth. And since that's going to be in Q, which is charge, that's coulombs. And a little later, we're going to learn about how to draw out what we call electric circuits. And there's like symbols. This would be like a wire. But a capacitor is two lines on either side, because this is going to have the positive charge and this is the negative charge. And then when the capacitance builds up enough, it jumps across and then it kind of shoots the energy out. This is, by the way, used on defibrillators, right? You've probably seen this in the movies, and I hope you've never seen this live, where they say, back up, charging! They're charging the defibrillators when they're about to, shock somebody's heart back into, existence. And it's when there's that sudden release. It has to build up, and then when the capacitors discharge, then the electricity flows very rapidly and through the system and hopefully saves the person life. Maybe a better way to understand capacitance is to think of a couple of buckets. All right? So if I've got a bucket of water, just water, right? The height of the column of water is the voltage. Remember, that's the joules per coulomb. But the capacitance all right, is the area. I mean, it's like the whole volume of the water. It's like the area of the surface area of the water. But if I were to have a second bucket, right, a narrower bucket, but this bucket is the same height, right, the water level is the same height, this would have the same voltage as this because it's got the same height, but would have a much lower capacitance. So let's go back to the concept of the capacitor. Remember, it's just two plates separated by a distance. One is positive and one is negative. So how can I make the capacitor like the highest capacitance that I can make? Honestly, it has to do with the charge. So the higher the charge, notice the charge will be the same on the positive and the negative. So if I got a bigger number of electrons, right, a bigger Q, if you will, then that's going to increase the capacitance. But the other variable is the distance between them. And this is the opposite. The closer they are together, the more they like each other, and the more they want to make the jump. So the distance goes down, the capacitance goes up. So how does this relate from an energy perspective, right? Capacitance, if you think about it, is something that I can do work with. If I have a capacitor, it can do cool stuff, right? It can run a defibrillator, et cetera, et cetera. And there's a couple of key equations that you're going to note. The one we've seen before, Q equals C times V. Capacitance voltage is the charge. But another equation that we haven't really talked about is this one, that the potential energy is equal to 1/2 times QV, right? Now notice we've got Q and QV, so we can actually like put the Q in here, so we can say that the potential energy is equal to 1/2, right, times Q, which is CV squared. You might notice that kind of looks like the equation. And so then, of course, we can then solve for like the amount of energy in something. So let's take this example right here. We've got a defibrillator, right? We've got a defibrillator, and we're trying to figure out how much energy, the potential energy that it's going to have, or it could be converted to kinetic energy as it's released. So what do we know about this particular defibrillator? We know that it has a capacitance of 175 microfarads. I'm just going to say 175 times 10 to the minus 6th farads. That's the C. We know the voltage, very high, right? 2,240 volts. That's here the problem, right? And we want to solve for Q for PE. So for Q, we're just going to multiply these two numbers together. So Q would be equal to 175. And we get 0.392 coulombs, right? When we multiply these two numbers together. Get your calculator out, trust me. Now if I want to find what is the energy of that system, that's equal to 1/2 times Q, which I got right here, right? 0.392 times the voltage, 2,000. And we get, multiply these all out, you get 439 joules. So in the defibrillator problem, we can find out how much energy is going to be passed through the system to restart the dude's heart, right? That's a lot of voltage, right? And this is going to be the amount of the energy and also the number of coulombs that are going to pass through the heart in a defibrillator. So you can see how capacitance right here is the bomb, right? It helps us to figure out how much stuff, how much energy, how much like power, that's not power really, how much energy can pass through a system if you let it, right? Again, and it's designed, it's a super simple like design. Two plates, one's positive, one's negative, you charge them, and then when the electrons jump, that's when the capacitor is released. Houston, we don't have a problem. We'll see you in class.